So, we have from purely kinematic consideration have already established that in general the fluid velocity is coming from three different contribution. One is an isotropic expansion, one is a rigid body rotation, and the third is sum together of uniform velocity plus a straining motion without change in volume. So, we have now discussed to find how to find the velocity field if the rate of expansion is specified everywhere, if the vorticity is specified everywhere. So, what left is how to find the velocity which is associated with a pure straining motion without change in volume. If you remember, we mathematically wrote that velocity field in general is u e plus u v, where u is the part that gives the rate of expansion, which we can obtain if the rate of expansion is specified everywhere. U v is the velocity contribution coming from the rotation, rigid body rotation, and we have seen that this also can be found if the vorticity is specified everywhere. And the last part which is associated with a pure straining motion without any change in volume. This part, by definition, that this part is now is not associated with no expansion, associated with no vorticity. That is, there is no expansion associated with it, there is no vorticity associated with it, or other way that both divergence of V equal to 0 and curl of V equal to 0. So, this is the part of the velocity which is without any expansion, without any rotation. And now, we will try to say something how to find it, but before doing that, see one thing in particular. If the flow is incompressible, then this total velocity or the actual velocity u, that itself satisfies divergence of u equal to 0. You know that for incompressible flow, and we also know that for incompressible flow there is no rate of expansion. For incompressible flow there is no rate of expansion, that is what it means, this equation divergence of u equal to 0. That is, this u e component is not present in incompressible flow, it will not be there. Now, if it so happens, I am saying if it happens that in particular cases the incompressible flow is such that its vorticity is also 0, then what happens? Then this u and v become same. Okay. and in that case the velocity field is simply solenoidal and irrotational, both are satisfied, divergence of u is 0, curl of u is 0. At this stage of course, we will not be able to tell it definitely, but I will just tell you that you might have a question that what is the utility, because in aerodynamics we are mostly concerned with gases, and gases are highly compressible. So, why we are interested in incompressible or a solenoidal velocity field? However, that is not true. In many practical cases, we will see later on that under certain conditions, which are quite common, under certain conditions all flows can be treated as incompressible and the velocity field to be solenoidal. And there are many common situations in all practical problems where the most part of the flow field is irrotational. So, even though it looks that these are too highly simplistic, the flow field is solenoidal and irrotational, but they are not uncommon. There are many practical situations where these are quite acceptable, that the flow field is almost solenoidal as well as irrotational. And it is then highly important to discuss about this type of flow. In the first look or first glance, it may appear that it is not a real situation, at least in aerodynamics, where we are mostly concerned with gas, but later on we will show that that is not so. Even in flow of air or flow of any other gases, there are many situations where the flow field can be considered almost incompressible and the velocity field to be solenoidal as well as irrotational. Now, since we will work again not in terms of u, but in terms of v, that is considering is one of those three contributions. Since we have divergence of v equal to 0 as well as curl of v equal to 0, since curl of v equal to 0, we can show that over any open surface, think about any open surface, or let us say curl of v n d a, where this area A, area is completely immersed within the fluid, it is within the fluid, then this integration will be what? And this is 0, curl of v is 0 everywhere. Now, think about any two curve, or let us say consider any 2 points within the fluid, and then consider 2 curves that joins these 2 points, and let us say that these 2 curves form a reducible closed curve, like say this 2 points say O and P, and say one curve and other curve. Then what this equation gives? Agreed? Provided that C 1 and C 2 forms a reducible closed curve. If the curve once again to remind you what is this reducible closed curve, a curve will be called reducible if it can be shrunk to a point without going out of the domain. So, in this case any curve within a fluid can be called reducible if this curve can be shrunk to a point without going out of the fluid. And we can see that in this case if the interior is just fluid, we can very easily shrunk it to a point just by deforming. Think about say aircraft wing, we have a curve around that aircraft wing. Is it reducible or not? Is the curve reducible or not? It is reducible. Let us say we have this I have this pen in my hand. Okay. Think about a curve around this pen. Is that curve reducible? Yes or no? Why? Can't we shrink it to a point without going out of the domain? So, this everything is the domain here, from here to infinity in all direction, that is the domain. Can we shrink the curve to a point? Yes, we can. The curve is here, let it slide here and then shrink. Finish. So, same thing if it is an aircraft wing or say an aircraft. A curve rounding it, we can slide it so that it goes out of the wing and then shrink it. So, if there is a 3-dimensional object within a domain, in a 3-dimensional domain we have a 3-dimensional object 1, then all curves are reducible. We can simply slide it and do it. We can't do it in case of 2-dimensional. By our definition, a 2-dimensional say wing means a wing which is infinite in this direction. So, we cannot slide it out of the wing. We slide it, it is still there, the wing is still there. So, in a 2-dimensional case we cannot have all reducible curve, but in the if there is a 3-dimensional body within the domain, which is actually our interest. In aerodynamics we will have the aircraft or say a wing and then the atmosphere, the fluid air. See, in our case the fluid domain is the entire atmosphere and there is another the wing is a boundary of that fluid. The other boundary perhaps we will consider somewhere. So, we are not going out of the boundary, but if it is 2 dimensional, then we can't do it. We have to go out of the boundary. If we want to shrink it, we have to go out of the boundary. However, there might be some other curves which are not enclosing this object, that can be shrunk. So, there are different curves which can be shrunk, which cannot be shrunk, but in case of this other type of domain, wing within the infinite atmosphere, in that case all curves can be shrunk, all curves are reducible curve, but if it is 2 dimensional wing, then all curves are not reducible curve. There are some curves which are not reducible, there are some other curves which are reducible. Any curve that loops the wing is not reducible, but any curve that does not loop the wing, that is reducible. So, we have these two concepts, reducible closed curve and irreducible. Now, since we have this curl of this velocity v is 0, again from vector algebra we can write that v must be gradient of a scalar function. If the curl of any vector is 0, then that vector must be gradient of a scalar. Okay. So, using that, this function phi is called potential. Do not associate it with energy in this case. Now, using that relation what we earlier had, can you write that phi x, this is the point say x and this is the point x 0. So, phi x is and see this is true for any two path which forms this reducible curve, the difference. And in that situation, that is where the paths are reducible, in that case this phi becomes a single valued function, that it has only one value. At each point it has a fixed value. However, if it is not, that is all curves are not closed, then it is not essential that phi has to be a single valued, phi might be a many valued function. If we can have some irreducible curve, then the single valuedness of phi is not guaranteed. In that situation, phi will be a many valued function. Now, let us use this definition V equal to grad phi and substitute it in that solenoidal condition, divergence of V equal to 0. What do we get? We have divergence of V equal to 0 and we substitute V equal to grad phi here. So, when the velocity is irrotational and solenoidal, this is the equation that helps to find the velocity field, the velocity. Instead of 3 unknown, we now have only one unknown. This is scalar. The velocity has 3 components, so 3 unknowns, but now we have a potential which is scalar and a single unknown. So, instead of that 3 unknown, we now have a single unknown. Okay. This equation particularly, this is called Laplace equation. This Laplacian operator is simply this. In Cartesian system is this is the Laplacian operator in Cartesian coordinate system. So, this is basically a second order partial differential equation. Second order partial differential equation. The equation is linear with constant coefficient. All these terms have constant coefficient 1. So, this is the some mathematical nature of this equation, that this is a second order linear partial differential equation with constant coefficient. We earlier also had this type of equation which we named Poisson equation, in which case the right hand side was not 0. If you remember that both u e and u v satisfies that type of equation. Eventually, u e is also associated with a phi, that time we wrote a phi e. If you look back, u e we had a phi e associated, but in that case the governing equation was not Laplace equation, rather it was a Poisson equation, on which the right hand side, left hand side was similar, but the right hand side was non-zero. Laplacian of phi equal to something, and because of that we have been able to find a single solution, one solution only. Same thing happened in case of the u v, the vorticity associated velocity. There also we had a governing Poisson equation. The right hand side was non-zero, an inhomogeneous equation, which made it possible to have a single solution. Solution for phi e in case of u e and solution for b v in case of u v. A single solution was possible. However, in this case this Laplacian phi, the right hand side is 0 and there are many functions which satisfy this equation. As an example, you can try that 1 by r, 1 by r square, 1 by r cube and so on, all of them satisfy this, any of these functions. So, you do not know which is our solution. And not only that, see, the equation is linear, linear. So, if you have any solutions, they can be summed together to make another solution. So, phi equal to 1 by r is a solution of this equation, phi equal to 1 by r square is also a solution of this equation, hence 1 by r plus 1 by r square is also a solution of this equation. The solution of these equations are usually called, say harmonic functions. The solutions are harmonic functions. However, there are some other important thing associated with these equations. These equations, these partial differential equation or Laplacian phi equal to 0 or show even that Poisson equation Laplacian phi equal to something non-zero. In these equations are called elliptic type of partial differential equation. Okay. Partial differential equations also can be classified in 3 category. You will be doing it in your mathematics course, I hope, and again they are named following those conic section names: elliptic partial differential equation, parabolic partial differential equation and hyperbolic partial differential equation. They have different properties. As an example, what I will tell you here or what is relevant in this case, that solution of elliptic partial differential equation are smooth and continuous function over the entire domain. Solutions of elliptic partial differential equations are smooth and continuous function over the entire domain. So, since in this case this particular elliptic partial differential equation has resulted in case of a solution of irrotational solenoidal flow field. So, what we can say that the irrotational solenoidal flow field is smooth and continuous over the entire domain of the flow. No discontinuities or no jump is permitted anywhere within the fluid domain. However, they may be possible if there is some sort of discontinuity or some sort of thing is specified over the boundary. As an example, I can tell you, say like if you are thinking about flow which involves a corner, you know at corner there is a jump in the slope of the geometry. So, if you are specifying that type of boundary, in that case at that corner some sort of discontinuity may be possible, otherwise it will not be possible anywhere. The solution has to be continuous and smooth everywhere. Then, however, the hyperbolic partial differential equation on the other hand even allows discontinuity within the solution, within the domain itself. So, in a problem where there is the governing equation is an hyperbolic partial differential equation, you may expect a jump or some sort of discontinuity. As an example of hyperbolic partial differential equation, you must have come across wave equation or the vibration of string, that is also an wave equation. So, in that type of situation this jump or discontinuity is possible. Again, to solve an elliptic partial differential equation, conditions in all the boundaries must be specified. They are essentially boundary value problem. Wherever there is a boundary, the conditions must be specified there, and the entire domain must be solved together. The entire domain, the solution for the entire domain must be together. While in case of a hyperbolic, if the governing equation is hyperbolic partial differential equation for a problem, in that situation it is not essential to specify boundary condition in all the boundaries. The initial condition is important, the final conditions are not, they are not required. And it is possible to solve part by part. You can proceed as a solution. However, that is not possible in case of elliptic partial differential equation. So, these are then, since the solenoidal irrotational velocity field satisfies such an equation, we can say these are the general property of the solution. We cannot have a unique solution unless something else are given, as in case of the velocity field associated with specified rate of expansion or specified vorticity, we had a unique solution. In this case, we do not have a unique mathematical solution here at this stage. There are many functions, all called harmonic functions, which satisfy this Laplacian phi equal to 0 equation, and any one of them can be a solution for a given problem. Without knowing something more, we cannot tell what will be the solution for a particular case. We had a general solution for u v and u e, but for this b we do not have a general solution. Simple general solution does not exist. Also, the solution of this equation depends on the topology of the geometry, what type of geometry we are having, or what type of domain, fluid domain in this case we are having, which I have already mentioned that if phi is single valued or many valued, or in other sense whether the region that we are solving, whether that region is singly connected or multiply connected. Are you familiar with this simply connected and multiply connected domains? A simply connected domain is that in which all curves are reducible. Any set of curve, any set of closed curve are reducible, and a multiply connected domain is which is not singly connected domain. There are some set of curves which are not reducible. As a specific example to flow problems, like flow over an aircraft is a singly connected domain. The domain is singly connected because all curves are there reducible curve, as we have discussed. Flow over a sphere, again the domain is singly connected. Flow over a finite cylinder, again the domain is simply connected, but flow over a two dimensional cylinder, the domain is not singly connected. Flow over a three dimensional cylinder or is singly connected domain, but flow over a doubly connected or sorry two dimensional cylinder, then the domain is not singly connected. Flow over a two dimensional wing, which we usually call airfoil, flow over an airfoil is flow in a doubly connected domain. We will tell later on what are doubly connected and other. However, flow about a finite wing is flow in a singly connected domain. Flow about a wing with slat and flap deflected, flow over a three dimensional wing with slat and flap deflected is again flow in a singly connected domain, but flow past an airfoil with its leading edge slat and trailing edge flap deflected is multiply connected, eventually fourply connected or quadruply connected. And the difference is that in case of singly connected domain, phi is a single valued function. If the domain is not singly connected, phi is a multi-valued function. Now, of course, trying to solve this equation will take little more time. Before that, we will be doing something else, but other than this some general nature of the solution, that what type of solution we are likely to expect and what will be the behavior of those solutions, we will do one thing more as far as the solution of this equation is concerned, that is the uniqueness. As we said that there are many functions which satisfies the equation Laplacian phi equal to 0. Now, think that we have a flow problem, a real flow problem, where this v is not just one of the contribution, rather it is the velocity. As we said that it can be, if the flow field, if the actual flow field is inviscid, or forget it, inviscid, if the actual flow field is solenoidal and irrotational, then this itself is the total velocity, this is the velocity. This is the flow velocity. Then in a physical problem, as you can understand that the solution must be unique. A physical problem will not have 2, 3, 4 solutions. A physical problem always has one solution. The mathematical problem may have many solutions. Then what it is that is making that the solution is only one, not so many? Because the equation is correct, equation is representing a solenoidal irrotational flow, and there are some problem, physical problem, which are very close or say nearly perfectly solenoidal and irrotational, and that physical problem has one solution, while the mathematical problem have many solutions. So, of course, all those mathematical solutions, not all those mathematical solutions are the real solution. There is only one which is the actual solution, the others are just spurious or mathematical solution, or there might be something which will make the solution single, unique. So, we will try to look for the uniqueness condition, that what it is that will make the solution unique for a given problem, that the solution will make it unique. First of all, we will consider a singly connected domain, uniqueness condition in singly connected domain. Then we will go for multiply connected domain. It is also called simply connected domain, singly connected domain as well as simply connected domain. We will start with this mathematical identity, divergence of phi v, or say forget about the integration first. Divergence of phi v, what it is? Phi is a scalar, v is vector, as you are using. Can you say what this relation will be? Divergence of phi v. It is grad phi dot v plus phi divergence v. Now, we have grad phi is again v. So, it is v and this is 0, divergence of v is 0. So, this divergence of phi v has become v dot v. Now, we will apply divergence theorem to this problem, that is, we will try to integrate it over the volume and then that integration will express as surface integral. For that, let us consider this domain, that we have a boundary, okay, and also possibly as well as some internal boundary also. So, this is the region that is occupied by the fluid, but the domain is singly connected. Okay. At least it is not 2 dimensional. 2 dimensional domains are never singly connected. So, it is actually 3 dimensional, just a representation. This is what is the fluid region. So, when we call the fluid domain, this is actually the domain, not this part. This is a boundary and this is the other boundary far away. Let us call this surface area, surface is A1, this surface is A2, this is the volume V, and consider outward normal with respect to the boundaries. Now, let us write this mathematical relation or the volume integral sorry. What it will be? What this will be? Apply divergence theorem. What is this? We want to express it as a surface integral. So, what it is? what is the surface of this volume? That is sum of those two surfaces A1 and A2, that is the boundary surface for this volume V. So, the surface integral now will have two terms, one for surface A1, the other for surface A2. And okay, let us N2 is here. So, it will be what? Phi V dot N2 dA over A2, or you can write dA2, it does not matter, minus phi V dot N1 the 2 has different sign, because with respect to the fluid domain the 2 normal has different reaction, one is outward, one is the other is inward. We have taken 2 outward normal with respect to the boundaries, but with respect to the fluid one has become inward, the other has remained outward. So, that is why the 2 signs are different. Now, we see a special situation. Think that this V dot N2 is a normal component on the surface A2, okay, normal to the surface A2, and V dot N1 similarly normal to the surface A1. And if both of them are 0, if both of them are 0, that is both the boundary surface have no normal velocity, both the boundary surface have no normal velocity, then what will happen? Then V is 0. If both the boundary surfaces have no normal velocity, then this V is 0, or other way, that a solenoidal irrotational velocity is not possible if both the boundaries are stationary. If both the boundaries are rigid and has no normal velocity, then the fluid contained between these two rigid boundaries will have no solenoidal irrotational velocity field. Anyway, so what is required, that to have some solenoidal irrotational velocity flow field, at least part of the boundary must have some normal velocity, part of the boundary must have some normal velocity, otherwise no solenoidal irrotational velocity field is possible. Now, just to check for uniqueness, let us consider that we have two velocity field V1 and V2 and two corresponding potential field phi 1 and phi 2. Since the equation is linear, then the difference of these two solutions is also a solution. So, if we have two solutions, say V1 and V2 and corresponding potential as phi 1 and phi 2, then V1 minus V2 with associated potential phi 1 minus phi 2 will be another solution. So, let us take then that, let us take, I do not know, two solutions, V 1 associated with phi 1 and V 2 phi 2. Then we can write this, that V 1 minus V 2 dot V 1 minus V 2 integrated over the volume V is phi 1 minus phi 2 into V 1 minus V 2 dot N 2 dA 2 minus we have substituted phi 1 minus phi 2 and V 1 minus V 2 in this equation. Okay. In this equation we have substituted these. Now, if our solution is unique, if the solution is unique, then phi 1 minus phi 2 and V 1 minus V 2 must be 0. The solution will be unique if V 1 and V 2 are same, phi 1 and phi 2 are same. And how will that be possible? How will that be possible from here? Can you tell? Looking to that, can you say how can that be ensured? That will be possible if V dot n is specified, if V dot n is fixed. Alternatively, if phi is fixed on the boundary, if V dot n on the boundary or phi on the boundary is fixed, either of the two or a combination of the two, that on some part of the boundary V dot n is specified, on the remaining part phi is specified, then also it is possible. So, in a problem where V dot n is specified, the problems are called Normin problem. Problems are called Normin problem, or this, see, this is a condition on the boundary. So, they are called boundary condition. This particular type of boundary condition where the normal component of the gradient of the unknown function is specified. In this case, of course, it is the normal velocity, but this might be any general problem, Laplacian phi, it might be any general mathematical problem. Rather, this is very common equation in almost all branches of science, Laplacian phi. In many cases it comes. Of course, the phi has different meaning in different situation, and in all cases this is general, this is mathematics, there is no fluid mechanics or anything. So, these are general. So, if the normal component of the gradient is specified on the boundary, that type of boundary conditions are called Neumann boundary condition, and then the problem is called Neumann problem. Okay. So, this is Neumann condition or Neumann problem. In a situation where the unknown function itself is specified over the boundary, that is called Dirichlet problem. And the last one is, of course, a mixed. So, when these conditions on the boundary will be specified, the solution will be unique. So, only those solutions which will satisfy these conditions, they are the actual solution.